afternoon. This is CIVE633, Environmental Hydrology. Today is Thursday, November 4th, 2021. And this is the second session or second lecture of the 11th week. We only have 4 more weeks to go, 4 more weeks of lecture, and then 2 weeks of finalizing the class. The subject today is the flood pulse in the river continuum. That's only one or two papers out of 3 or 4 or 5 that we will review today. So let me just get started with it. I think I don't need this over here. I need this, and then I'm going to share the screen. We should share the screen in here. Yeah, that's right. I'm going to share this screen in here.
Professor Ponce, I just logged in.
Who is this?
This is Sarah McGaw.
Sarah McGaw. Okay, cool.
Thank you.
Is more there? More? More's not there. Okay. So let's keep going in here. There's two papers in here. One is called the river continuum concept, and the other one is called the flood pulse. These are concepts of hydrobiology, or also what's the name? Limnology. Limnology is a subfield of ecology that studies life in bodies of water. That's limnology. Now, there's also a related field called hydrobiology. And since we now realize, engineers now realize, that there's life in rivers, right? The first thing that led us to that discovery, if I may say so, was the construction of the dams on the Columbia. The Army Corps of Engineers over the 30s and 40s and 50s and even to the 60s, 70s actually, developed the dams on the Columbia. There's many, I don't know how many, maybe at least 10. One of them is that I visited in the year 2014 was Bonneville Dam. Then subsequently realized that there were fish on the river, salmon and so forth, and they had to go back in there and re-engineer the dams to make it possible for the salmon to climb the dam. The salmon couldn't climb the dam was too high. So they built a series of fish ladders, which were presumably, according to the reports, very effective in actually allowing the salmon to climb the dam. And this is just one extreme example or big example, or I could say important example, of how rivers, the realization by engineers that rivers do actually have biota in their fish, all kinds of biota in rivers and lakes too. And that we, when we look at hydrological issues, we need to consider the biota. That is a fact. So there's these two concepts in here that I'm going to discuss with you today, which were developed by people that are ecologists, river ecologists, or as I said, limnologists. One of them, his name is, I can't remember his name right now. Let me go back in here. His name is Sedell, the river continuum concept. And then opposed to that concept is what has been referred to as a flood pulse. And that is by Professor Junk from Germany. I visited, actually, I have a personal note. I actually visited Junk in the year 2000. No, it was not 2000. 1994, and actually met with him out there in Germany somewhere. But let me just go back. Let's not get sidetracked with the stories in here. River continuum concept. This is the first concept that is opposed to the flood pulse. So if a river is studied or analyzed, and then the RCC, it does not is not analyzed under the FP, which is the flat pulse. So let's take a look at how these two systems may differ. And let me also say that this is an ecology concept. So it's a little bit strange for us engineers. These people don't put a whole lot of numbers into their thought. Okay, we do. We have a tendency, that's by training, to not accept anything if it doesn't have some numbers. But in here, no, we're just talking in general. Okay, so there's a difference between small rivers and large rivers. That's true. The small rivers have a tendency to be somewhat longitudinal in features, right? Yeah, the rivers are longitudinal, but there are rivers out there that are very large that have features that are transversal, not longitudinal, and that's the whole point of this issue here. So we can set them apart. Small rivers are the ones that have a tendency to have longitudinal features, and not only geomorphological or fluvial geomorphology, but also in their biology. The transfer of energy and so forth that the biologists describe is done in a longitudinal fashion as opposed to transversal fashion. Okay, ecological perspective, from an ecological perspective, that includes productivity, carbon dynamics, nutrient cycling, biodiversity, hydrologic interactions. Look how they put hydrologic interaction at the end. And hydraulic effects at the end. There's a difference between hydrology and hydraulics. Dams come in and kind of change things, and we do that, all the time. There's probably 60,000 dams in the United States and about 200,000 around the world. Large rivers have frequent transversal interactions. That's true. And we will get a little bit into the diffusion concept later on, which these people don't get because they obviously don't manage that subject. So the river continuum concept, or RCC, treats the river as a continuous series of physical, chemical, and biological adjustments along the length of the river. That's very important. Uh, Longitudinal elements in which the processes in downstream reaches, there's misspelling in there, are linked to those in the upstream reaches. So goes from upstream to downstream. Uh, can the RCC explain the behavior of large rivers? We think not. These people also don't think so. There's biological, ecological behavior of the large rivers are not subject to the principle of the RCC. Okay, let's keep moving along and hear what Sedell said. Actually, Sedell wrote a paper in 1993 or 1994 that I had a chance to read, and I just summarized in here very, very quickly, or rather very succinctly, what the major issues that he had raised. The RCC provides the most useful predictions of longitudinal lotic system characteristics. Lotic is river, lentic is lakes in ecology. Interaction with the floodplain, predictions is not as good. That's right. So if there's a large floodplain, the predictions are not good. Amount of floodplain interaction is constrained by geology and geomorphology. True, the two basic earth sciences. Large variability of depths, widths, and velocities lead to increased productivity. That is a truism. Where there's diversity, there's increased productivity. That's just the way Mother Nature put it together. Because of the competition between the elements of the species and so forth. There's more diversity, there's more competition. The RCC is a limited value for predicting large ecosystems. He did say that. Research challenges to determine how ecologically important processes at the reach level can be meaningfully aggregated to large river systems. That's good. How do you integrate from the reach level to the large river system? And finally, he talks about the interaction, which we defend all the time, interaction between the disciplines, the ecologists dealing with the actual life processes or ecosystems, ecosystem dynamics within the river itself. The fisheries biologists, those people interested, or biologists interested in figuring out how much fish is there, if they can perhaps extract it, take it out, or whatever, fisheries. Biogeochemists, these people are the people that study the nutrient cycles, biogeochemistry. Atmospheric scientists, engineers were there. Geomorphologists, which is kind of an in-between, and hydrologists, which is also in between. Interesting to mention that geomorphologists and hydrologists could belong to three categories. They could be engineers, like me, for instance, or they could be geologists, or they could be geographers. There's some geographers out there that do extensive geomorphology, by the way, and hydrology. Why not mention it? We have in our San Diego State, we have a Department of Geography, and I believe that there's a very large department, by the way. They have more than 20, 25 faculty. And I think they have 2 or 3 hydrologists out there. Anyway, so let's move on to what Professor Junk says. And I say junk because junk doesn't look good or doesn't sound good, right? In German, it's junk, like that. I'm not exactly sure of the pronunciation, but that's the way it is. It's certainly not junk. Okay. Hydrologists think of river as longitudinal links, but that's not quite correct in all cases. There are significant transversal components. That is true. That's Junk's, how can I say, reason to be. He's a defender of the flood pulse. He wrote a paper in 1989 talking about this and making what it's supposed to be. It should be a big deal because most of the times it had been, up to that time, it had been ignored. And I remember when I was in Mato Grosso in 1993, I believe, I remember I did tell you no, maybe in the other class, that I went to Mato Grosso and I gave a lecture on hydrology to biologists. And a person over there, one of the professors asked me what I thought about Junk's flood pulse concept. And she got me by surprise because I did not know, even in 1993. Well, it was only 4 years, but it's still, right? Research is research. So I had to go back into the books and find out, not to look dumb. And I found out, and this actually, my interaction with the people out there in Mato Grosso has really enriched me. What can I say? But it was not their fault or the reason because of that. I went there in 1979 on a contract to do modeling. And then eventually I ended up being associated with a whole bunch of people out there and learned a lot from them. Okay, river floodplain systems provide important habitat for biota. Right, exactly. The issue is how often is the floodplain used? That is the issue here. If it's every year, then there's a lot of transversal interaction. If it's every 100 years, as Professor Gilbert Thomas from Colorado would like us to believe, and I'm going to tell a story about that later on, then it's only 100 years. It's not every year, right? Ecology is divided into terrestrial and aquatic. Water bodies traditionally divided into lentic, which is lakes and ponds, and lotic, streams and rivers. Floodplains do not classify readily. Yeah, floodplains, what are floodplain? It's in between, it's a transition, right? So there is a term that ecologists use, which is called the ATTC, which refers to aquatic terrestrial transition zone. It's used to describe the seasonally inundated floodplain. Evidence of enlarged rivers supports a concept different from the RCC. Right, the flood pulse. It's different, totally opposed to the RCC. Let me also say that we've been talking about rivers here in Brazil, the Amazon, and so forth. And the question is, of course, for us is, do we have those kinds of things here in the United States? And the answer, of course, we do. We have the Mississippi. The Mississippi covers 50, 60% of the United States, and it's an extremely huge floodplain. We, of course, didn't like it. And for 200 years ago, been trying to eliminate the floods on the Mississippi, which has been very counterproductive. Of course, at the time, we didn't know, like everything else, right? 200 years ago, we didn't know. We thought we could solve the problem by building a levee. And we started building levees almost as early as the Republic. We've been building levees for about 250 years. That's been documented by McPhee and others. Very good book by McPhee, by the way, on this subject. And so we've been doing this for 250 years, and it has been proven difficult to backtrack. And if you look at the web and look at the Mississippi and what's going on, there's all kinds of arguments as to should we backtrack and how we're going to do that and so forth, and all kinds of issues out there on the issue of whether the levees on the Mississippi should have been built or not. They were built for 200 years, and they're still there, by the way. And for us to remove those levees just because Professor Ponce or somebody else said it or Junk said it, it's not going to happen. Okay, because what took 200 years to put together is not going to take a year to undo it. So we'll have to think about it. The future generation will have to cope with this issue of what to do with the levees. But the point is that all that sediment that was supposed to go into the fields of the Mississippi ended up downstream at the mouth, creating different situations. And sediment is gold, by the way. I lots of stories about that. I'm not going to get you into stories because we won't cover the material. Okay. The flood pulse, major force. The flood pulse is a major force controlling the biota. That's what I believe the term flood pulse belongs to Jung. Lateral exchange, more important than longitudinal supply. Large rivers with floodplains, the majority of the animal biomass derives from production in the floodplain and not from the downstream transport, because the floodplain is more extensive. Whether a river has a floodplain depends on stream order, geology, geomorphology, discharge, continental location. It depends on a whole lot of things. But some rivers do have a large floodplain. The Amazon is one of them. The Paraguay, the Upper Paraguay, where I worked for several years now. I worked for 17 years on the Upper Paraguay. Uh, it's the example of a floodplain, because when the Upper Paraguay floods, it covers 80 kilometers of width, not of length, of width. The length is about 700 kilometers, but the width is about 80 kilometers. It's a river outside of the books. It's certainly outside of my book. I wouldn't even consider even talking about that. Besides, my book is not on geology, it's just straight classical hydrology. Most tidal rivers have floodplains. The tidal estuary, it's a different thing. Because by the time the river gets close to the ocean, um, because of the concavity of the profile due to the law of sedimentation, it would have to become concave, and then it starts spreading its flow, and it has the shape of a triangle. The tidal estuary has the shape of the triangle. It opens up, it redistributes instead of distribute. Like, in other words, when the river from its morphology standpoint has three sections. The section upstream where everything concentrates, the section in the middle where it transports, and the section downstream where it opens up and undoes itself and redistributes itself over the estuarial floodplain. Um, Rivers with geologically induced continental deltas like the Upper Paraguay have extensive floodplains. I may have added this in here. I'm not sure that Jung did that work. June is an expert on the Amazon, but not on the Upper Paraguay. No, I take that back. He did quite a bit of work in the Upper Paraguay too. I visited with him when I was there, as a matter of fact, too. Uh, Geologically induced continental delta, what is that? Of course, right. The Upper Paraguay is there only because there was an uplift of 40 meters, maybe, I don't know, 100, 200 million years ago, and it created a continental delta. The Upper Paraguay is a delta, but it's inside a continent. So it's an unusual delta. We call that a continental delta. Runoff diffusion, that's my word, of course, I added that. Runoff diffusion will determine to a large extent the existence of a flood pulse and consequently of a healthy floodplain. Runoff diffusion is a function of the prevailing slope. Here we bring in the Hayami formula, which you guys may not know, because I've been talking extensively about the Hayami formula in the other class, not on this formula, not in this class. But if you took hydrology, you already know the Hayami formula. The Hayami formula says that the coefficient of diffusivity is equal to the discharge per unit of width on the channel divided by twice the slope. So if the slope is zero, the diffusivity is infinity. And now, of course, there's no such a slope of zero. But if the slope is very small, like in the case of the Paraguay, is 0.401, the diffusivity is very large. That's the smallest slope of a river that I ever saw, 0.401. Okay. The active floodplain is an area flooded by a 100-year flood. But that's, of course, that's an American definition. That is ascribed to Gilbert Thomas, and we'll talk about the story of Gilbert Thomas later on. We better hurry here, otherwise we're not going to cover the material. The period, according to Jung, the period is arbitrary and has little ecological meaning, and he is correct. Floodplains, areas that are periodically inundated by the lateral overflows. Their biota responds to morphological, anatomical, physiological, phenological, and ethological studies of animal behavior adaptations and produce characteristic community structures. The floodplain or the floodplain area is the ATC. The hydrologic unit is termed the river floodplain system, includes lentic, lotic, right? You can get out there, all kinds of stuff out there. Wetlands, lakes, and rivers, side rivers, etc. Hydrology. Number of floods per year will depend on the size of the basin, precipitation, geomorphology, continental location. Like in the upper Paraguay, there's one flood per year. There's only one flood. It's the minimum. You cannot have one. You cannot have less. You can have lots of floods, but one is the minimum. The Amazon, apparently, I haven't looked at the data recently, has two floods. One flood coming from the northern hemisphere and another flood coming from the southern hemisphere, which is interesting. Since they have different climatic patterns, it is understandable that that could happen because they have different timings. The southern hemisphere takes long to get there because it has to traverse the entire continent. Well, the northern hemisphere is right there, right next to the Amazon. So that's a lot shorter. It could reach the Amazon in a shorter time period, or exactly in a shorter time. The flood pulse characteristic of large river with seasonal floods. This enhances productivity, species diversity, and energy flows. That is true. Oh, here we go. Interruption of the flood pulse by anthropogenic action, meaning levees, will change the character of the ATC to terrestrial, reducing productivity, species diversity, and energy flows. In my opinion, we should have never done that. But who's Professor Ponce to tell the Army Corps 200 years later, you should not have done this? As a matter of fact, I'm not the one that's saying it. There's all kinds of people out there that are saying it. I was in the afternoon reading on the web, and you can just Google on the web, and everybody's saying their own thing out there. Finally, conclusions on the flood pulse. The ATTC, Aquatic Terrestrial Transition Zone, a pulse of long duration is characteristic of unmodified rivers. Aquatic and terrestrial productivity depends on the nutrient status, the climate, and the flood pulse. The flood pulse is dominant over the RCC and system with floodplains. That is true, and that's understood, and we agree with that. Processes in floodplains do not depend on inefficient processing of organic matter upstream. Right, the floodplain is self-contained. It doesn't need upstream help, while the RCC would actually need upstream help. It has to come from upstream, otherwise it doesn't happen, right? The flood pulse is its own house. And finally, the FPC should help in the hydroecological understanding of river floodplains. He's correct in there too. Okay, so now I'm going to go in here and I'm going to briefly talk about Gilbert White. Who is Gilbert White? Gilbert White was a professor of geography at the University of Colorado, I believe Boulder. And in the 50s, I believe he was hired by Congress to tell him what should Congress put on the law, because they were getting ready to put together the Flood Control Act of that time. We were going to control floods in the 50s, and it was going to be done by Congress, meaning Congress was going to put the legislation. So they hired Gilbert White, who was a very well-known gentleman at the time in the field of floods, geography. And he, later on, I think it was the year 2005, he must have been old by 2005. But at any rate, he was given, there was an interview by Martin Russ, I believe Russ or Russ, his name, and I believe the interview, let me see, the interview is on page 57. So let's take a look. Well, not there. Page 57. We got to go to page 57 here. There we go. We're right there. 57. See, I'm quick on this. The question, how do you take into account the so-called catastrophic flood, the once in 100-year flood? And this is what Gilbert White said. He said there was a very interesting development of the notion that there could be a flood of sufficiently low frequency that no effort should be made to cope with it. How interesting. We're trying to cope with the 100. He's saying the 100 is so high that we shouldn't cope with it. So this is just a view of it. You put a limit in there, and the question is whether you're approaching the limit from the left, from the right. But he did say from the right, I thought he would have said the effort should be made to cope with it, but not with the 200, right? That's what I always thought from our classes. Supposedly 100-year flood is the flood you're going to protect, okay? But he's saying, no, we shouldn't. We can do 50, we can do a little more, but not to 100 because 100 is too high. It's 4 generations. Federal insurance picked 1% of our recurrence. And some of them, the people that were making decisions at that time, were involved in that because we recognized they initially had to have some figure. You got to have some figure. The law has to have some figure. The 1% flood was chosen. I'm fascinated by what he said later. He said, I think Jim Goddard and TVA colleagues, I believe Jim Goddard was with TVA. TVA stands for Tennessee Valley Authority. Of the time, they were very big. Colleagues who would be considered parties to the crime. With the lack of any other figure, the concept taken from TVA's intermediate regional flood, in other words, a flood that is not too high and not too low, seemed a moderately reasonable figure. We generally use the term catastrophic flood for events of much lesser frequency, like 500 or 1,000 or even 10,000. Okay, so that's the story on Gilbert White. Unfortunately, he was interviewed before he passed away. Okay, I'm going to skip on these other 3 because we need to get going in here and finish. I'm going to go to Mainzer because it's very important. And I do hope that you can read Mainzer in its totality for whatever it's worth, for your education, if not for your instruction. I'm not going to quiz you on the what Mainzer said exactly in detail. He said a whole lot of stuff, which we have not really pursued to this point. Mainzer is respected by, we haven't really, the profession hasn't really paid too much attention. And you know why? Because he's in the crack. He's right in the crack between hydrology and biology. So the biologists don't like to look at it because it's not quite, and hydrologists either. So it takes somebody like myself or others, a few people out there that are looking in the crack so that we can begin to unravel what actually Mainzer said. Okay, so I'm going to read for you a couple of the pages only, okay? Perhaps the most outstanding feature of the flora of the desert is its relation or lack of relation to the water table. Why desert? Why Mainzer? Mainzer was a geologist, I believe, with the GS, with the Geological Survey. And he was given the job early 1927, I mean 1927 or 28, to research the water, the situation of groundwater in the western United States. You know, the Geological Survey is charged by the federal government or by Congress to inventory and tell us what is out there. So that's exactly what they were doing. They hired Mainzer to tell, so the Mainzer, I think it's Mainzer, to tell the country where is the groundwater, where is it on the surface, and where is deep and at what depth. Because in the eastern United States, the groundwater is very shallow because it's humid. I mean, you dig a hole within a couple of feet, you get the groundwater in there, and it's everywhere. Okay, so therefore there was no question about the groundwater. But in the western United States, you dug a hole of 10 feet and you couldn't find the groundwater. So therefore there was an issue of where is the groundwater? How does it vary? And of course it varies with the geomorphology. First with the geology and then with the geomorphology. But at the time, then there was a need to hire this gentleman. Okay. So on the one hand, there are plants which are adapted to extreme economy of water. These plants are referred to as xerophytes. Xerophytes. You know that. You heard about that term, xerophytes. Actually, phyte means plant. And the first word is a characteristic of the plant. And if you go out there to the web and try to look at how many phytes are out there, I've done it. I think I have that in some part of my website. There's about 25 of them. Xerophytes, mesophytes, hydrophytes, this phytes, that phytes, halophytes, appropriate for salinity and so forth, right? So as you can see, the issue with plants is endless. Humboldt said that studying plants was, somebody, I don't know if it was Humboldt, that said that studying plants was the most difficult thing because there were too many. You couldn't ever possibly learn all of them. And I think I told you, people have estimated there's 10 million species of plants out there. And they're all different, as you know very well. Habitually send the roots. These are he talked about the xerophytes. Now then he's going to talk about the phreatophytes. The phreatophytes are the plants that feed on the groundwater. And by feeding on the groundwater, they actually use groundwater. And actually quite a bit. The phreatophytes have become very effective because they have to fight, like everything else, you know. Not only do I have to pump it, but I have to pump it from wherever it is. So I better become efficient on it. So the phreatophytes became efficient. The term is obtained from two Greek roots that means a well plant. Literally a natural well with pumping equipment lifting water from the zone of saturation. Terms groundwater, zone of saturation are used in this paper. We already know that stuff. So what I'm going to do now is I'm going to go back. I should cut this thing. Let me go back in here. Where am I here now? Where am I here? I'm lost a little bit. Okay. I'm going to see which one is this. Okay, here we go. So I'm not going to get involved in reading all the stuff for you. I believe that you should. Okay. So evidence of the groundwater habit, right? There's plants that get into the groundwater. I'll extensively report on a paper that I wrote 2-3 years ago on this, which is somewhat clearer and to the point, and it's going to help us in a shorter time understand what exactly is going on in here. I'm getting a little bit lost on my own website in here. It kind of shows that I still don't know how to manage this. Okay, so I believe he poses a bunch of questions, and I don't know exactly where the questions are. Okay, here we go. See, I guessed this thing. Questions. We're going directly to the end product of what he was writing about. Questions that deserve further study. In regard to the groundwater, these are the questions he said. And he posed these questions at that time, 1927. What are the species that habitually depend on the zone of saturation? We identify those as the phreatophytes. To what extent and under what circumstances do these species grow where they cannot reach the zone of saturation? Meaning, can the phreatophytes be fed, like be irrigated? We don't know that. To be honest with you, I haven't gotten in there. To what extent will other species utilize water from the zone of saturation? And to what extent they are killed if the water rises to the roots? And he's asking the right question, because in nature, there's always, for the given moisture, there's a species. There's a species that have adapted over millions of years to the available moisture. If the available moisture gets reduced or gets increased, naturally or artificially, the species dies and it has to move. We have seen that in so many instances. There's a fight out there between the various types of species and where their domain is located. And if the domain changes, then the species have to move. Well, actually, they are kicked out. They die, and somebody else comes and takes their place. It's a fight. Like animals fight, plants also fight. We know that for a fact. Okay. Do they avoid the alkali in the soil by sending the roots into or nearly to the zone? I have to go back to the. I am totally at a loss in here. Okay, there we go. There we go. To what extent do the different species indicate the quality of the groundwater? That's interesting. I don't know. See, like I told you, many of these. He's talking correctly. He says, "Is there a different species that is actually adapted to different quality of groundwater?" He's correct. He knows what he's talking. How do they adapt themselves to the fluctuations of the water table? Some water tables fluctuate a lot, some water tables don't fluctuate, right? What are the conditions where there's a gravelly soil with a very thin capillary fringe as compared to a loam, which is a thick capillary fringe, right? Because the capillary fringe length or depth actually depends on the porosity. Actually, it depends on the size of the grains. If it's a loam, it's a silt, the capillary fringe could be 3 meters, 10 feet. But if it's gravel, it could be like 10 centimeters or 3 inches or so. It depends. There's a formula, actually, which I don't have it for you, but there's a formula in geotech that explains the thickness of the capillary fringe in terms of the diameter of the particles. What are the maximum and minimum limits of depth of the water table for different species? What is the greatest depth from which groundwater is lifted by the plants? That's interesting. I can tell you that it could be very deep. There's plants known to pump groundwater from 50 feet or more, 50 to 60 feet. Species that habitually send their roots to considerable depths. What adaptations have the young plants for enduring drought until they can get their roots down to the capillary fringe? So it's initial livelihood, like everything else in nature. You have to survive. If you don't survive, then you die and somebody else takes over. And I'm not going to continue in here. I'm going to have you work on this, by the way. I'm asking that you read this paper in its entirety so that you can get educated on the issues that were raised in 1927 by Mainzer, which are still issues that we need to deal with. Prior to the year 1900, actually it was around 1915, so it's 105 years ago, we didn't use groundwater. The pumps were not there. We used surface water. Then the pumps were developed, and then we had the fossil fuels coming in because you got to use the energy in order to lift the water, right? And then we started using pumps, and it became very popular to start pumping groundwater. It was around the 1915. There's a paper on it, by the way. There's a paper by Lee, 1915. At the beginning of the issues or the experience of society, U.S. and advanced societies that could develop and could use the pumps, right? Because these instruments, or rather pieces of equipment, were not being used in other parts of the world. Certainly not at that time. Undeveloped societies or primitive societies were using groundwater, but only the groundwater that was very close to the surface, which they could lift with a mechanical concoction, not by pumping using fossil fuels, right? I can tell you that when we did the study of Poway, we did the Poway study in the year 2012, groundwater study, groundwater sustainability study. We went into this place, we actually visited the entire area, and there was this house, it was kind of, I guess people had been living in that house for more than 100 years, and they had built a well, one of those round wells, and it was no longer being used because the groundwater had been depleted below the base of the well. But it kind of shows that the well was there. It's an old well. It looked like it was more than 100 years. So you can surmise that 100 years ago, the people out there used the groundwater by tapping into that well. Otherwise, the well would not be there. It's obvious, right? So wells were out there, but they were not pumped wells. The pump wells, 1915, roughly, on that order. So it's been 100 years. And then once we, society, decided that we were going to pump, we started pumping, selling the pumps, and now it's done all over the world. Okay, so that's the story of Mr. Mainzer. And, geez, I'm having a hard time today. So then the next reading that we have is this one over here. The choice between groundwater use and ecosystem preservation. The choice between groundwater use and ecosystem preservation. I should thank the people of Boulevard. Boulevard is a community of San Diego, southeast San Diego County, that supported me beginning in the year 2005 to work with them and funded, by the way. I was funded by them. Several funding occasions. I haven't done work there for 2 or 3 years now. Things have settled down a little bit. I don't want to get into that. But the point is that I worked in there from 2005 to 2018, roughly. Okay, it's interesting the way I got involved. We were working with the Campo Creek in the year 2005. And I had a couple students, grad students. And I wanted to go out there and check out Campo because I had heard that there were some levees and so forth that had been built in the land in order to hold on to the water. These are called retentions in the watershed, which are important because they retain the water, they pond the water, and they don't let it run off, and therefore they the land becomes more productive, right? Retention, water retention. So we went over there with these two students one morning, one Saturday, and we um, we were looking at it, and I suddenly realized that we were trespassing. We were in private property, and it's not a good thing to do. No, you don't want people to get into your property without permission, right? It's like somebody else intruded in my house in here and was standing in the back patio. Who are you and what are you doing here, right? So we were trespassing. So I said, we're going to run into trouble here because I have trespassed in many instances without really knowing, and I try to be careful about it. You can be shot if you trespass, and the wrong circumstances, you can be shot for trespassing. At any rate, so we headed to the house that was out there, the big house, and I said, this must be this gentleman or here that lives here must know who the owner or maybe they are the owner. So we went over there and knocked on the door, and this gentleman opened up, and I said, good morning. I introduced myself. I'm Professor Ponce from San Diego State. These are two gentlemen here, students, grad students, and we're here visiting, and we wanted to look at the meadows that you have over here, and I understand this is your property. He said, yeah, this is our property. We got 100 acres here. Oh, cool. Yeah, we're looking at the field. This is in the middle of Campo Creek in Campo, okay? And so then he said something interesting. He said, would you care for a cup of coffee? And of course, I know from experience that that's friendly. Nobody that is unfriendly is inviting you a cup of coffee. So I said, of course, yes, sure. So we went into the house and we had a cup of coffee, myself and the students. And then he said to me that he was the head of the water resources over at Campo Community Center or whatever. So he was an important gentleman in terms of water. So he wanted to get to know me because he knew I dealt with water and I was at San Diego State. San Diego State has a good reputation. So he said, we have a presentation by the county in a couple of weeks, and we would like you to be there also. Perhaps you can give us another presentation. Because at the time, in the year 2005, there was a fight out there. And the fight had to do with development of wells and whether the wells were going to start encroaching upon everybody else's rights and so on and so forth. Long story. Some people fight because they like to fight. But at any rate, the point is that he was interested in my contribution, so he invited me to give this talk. That was the beginning of my involvement with these people. I went over and gave a talk on sustainability. I knew sustainability, but I didn't know sustainability of groundwater. That's different. But I know enough groundwater to put it all together and so forth. These were going to be politicians anyway, just normal people, lay persons. So I wasn't going to be too technical. I knew that. So I gave a presentation. At the end of my presentation, this lady stepped over to me and said, Professor Ponce, I would like to invite you to my home because I'd like to show you a few things. I said, oh my, that's really friendly. So 2 years later, I was at her home, and I don't want to mention names, but she was the lead person out there, politician over at Boulevard. They don't have mayors, they just have various types of politicians, different names and so forth. So basically, she hired me. She says, I want you to do this work, and you do it. I said, sure. And that's where my involvement and learning, gosh, I learned so much in there. I have to be thankful to those people. They knew that I already knew 50%. They said, maybe you could learn the other 50, which I did, by the way. It's always the case, by the way. You never know exactly 100%. So let's take a look at what I did in here. Over out there was a ranch. As a matter of fact, this ranch is owned by this lady that I'm talking about. I don't want to mention names. And there was this tree, which is a very beautiful tree. When I went over there in the year 2005, 2006, it was beautiful. And in the year 2015, it died. I asked her, I said, one day I saw maybe 5 years ago, I went over there and the tree had been cut like you see there. It was a big tree and it was cut. So I asked her, I said to the lady, what's happened to this tree? And he said, it died. And I said, how do you know? That was a dumb question for me to ask somebody that lived there and knows about trees, not me. I don't live, I have trees here at home, but it's a different story. You know, we're urban, not rural. So she said, yeah, it's dead. I can tell you that a fact. We know when the tree is dead. That according to her, this tree died because of what we're pumping. It was drawing water from the groundwater, and the groundwater disappeared. It went deeper and deeper, so it couldn't pump it, and therefore it died. So there's one example. Based on this story, I decided to do this paper. So this paper was written 2-3 years later, in the year 2018. It's the choice between groundwater use and ecosystem perturbation. It occurred to me at the time something that it is correct, that if the groundwater is within the surface, within reach of the vegetation, if you pump the groundwater and lower the groundwater the groundwater level, the water table level, the vegetation is going to find itself hard to continue the pumping, and eventually, if the decrease in water elevation of the water table is large, then eventually bad things would happen, such as what happened to this tree over here. So, abstract. Excessive or unregulated pumping has the effect of lowering the water table and negatively impacting the vegetation accustomed to getting its water from the unsaturated zone or VADA zone. Excessive. What's excessive? Excessive is excessive. I mean, some people think this is excessive, other people don't think. So it's in the eye of the beholder. Unregulated? Has pumping ever been regulated? And the answer is no. Groundwater pumping is still unregulated. We have, I believe, Cassidy. Is it Cassidy that's going to work on this subject? Cassidy, can you help me out?
Yeah, that is me.
Yeah, exactly. Cassidy is going to give us the current story of the regulation in groundwater in the state of California. We're going to wait until the end of the semester. So she's going to talk about this important subject of regulation of groundwater. So groundwater is still to this point unregulated. The enlightened groundwater management must reach beyond hydrogeology to encompass the closely related fields of eco-hydrology and eco-hydroclimatology. Because I'm going to say something which is a truth, it's a hard truth, that the hydrogeologists don't really know about plants. And some people would argue that it's not in their training. They're trained to pump. They're not trained to not pump. So it's a good thing to hire a classical hydrogeologist to look at these issues of sustainability, because he would be thwarted. He wouldn't know what to do, right? The gentleman that most contributed to the sustainability of groundwater was my friend and colleague, Bill Alley, who was a head hydrogeologist for the USGS, and he was working here in San Diego, by the way. And he, in 1999, wrote a seminal paper on this subject, from which I learned. When I had to work at studying sustainability of groundwater, the first thing that came to mind was Ali's paper, because you Google it and Ali pops up immediately, right? Great paper by Ali. I learned a lot from him. But he was not a hydrogeologist. Ali was a surface water guy, like me, as a matter of fact. He wrote a bunch of papers on kinematic wave. Okay, so he had to do it because the other guys could not do it. Okay, this would prevent the anthropogenic aridization of the ecosystem. Right, if you kill all the trees on the surface, then the situation becomes more arid, among other things. I mean, there's only one thing, though, for the many negative aspects that could happen. So the question of how much water to pump from a shallow aquifer without encroaching upon vegetative ecosystems has no straightforward answer. Some people say we're going to pump deep, but you don't really know the connections. You don't really know the connections out there. You can pump deep and then end up filtering the water from the top to the bottom, and then you end up with less water at the top. Nobody knows the complete issue of the connections out there. It's underground. How would you know? Okay. There is a field that studies that, but they don't know the entire story. So enlightened groundwater management must reach beyond hydrogeology to encompass the closely related fields of ecohydrology and ecohydroclimatology. Okay, I have a story here, but I'm not going to tell you because we won't finish. Groundwater use. Societies have pumped groundwater for more than 100 years. And this you can read on your own. It's pretty much straightforward. Groundwater withdrawals. On the west, we pump more groundwater because there's less water and we rely more on the groundwater. And that is unfortunate because that kind of shows that eventually we're going to have to pay for it. I think I already told you that 45% of the water used in California is groundwater. I will feel more comfortable with a 5% figure or maybe 10%. 45 is high. That is why California is leading the U.S. in regulating the groundwater. And we're going to know the story. Cassidy is going to tell us her research, the product of her research. There's going to be regulation, but it's slow in coming. And I believe Cassidy told me the other day something I already knew, that the state has given itself 30 years to finish the project because they figured it's a tough subject. 30 years. For the next 30 years, a complete generation doing the thing without really actually finishing the regulation. Okay. So a third of the precipitation shows up as surface runoff. We know that, and we already discussed that. The remaining 2/3 return to the atmosphere via what we call vaporization, which consists of all kinds of evaporation from water, from vegetation, and from the land. Okay, the fraction of precipitation that infiltrates into the ground may follow two paths. It may move down in a predominantly vertical direction to join the groundwaters, or move up, returning to the atmosphere via vaporization, effectively short-circuiting the hydrologic cycle. In other words, infiltration does not all go into the groundwater. It can be pumped up by the plants and move back, right? And we recognize that that is exactly the process. This process was also Leibovitz in 1979 put numbers into this process. We already talked about extensively. Okay, so we have two types of streams in here that we need to look into because they're related to the groundwater. An ephemeral stream, which is the La Leche River in Lambayeque, Peru, there's no water, hardly ever water, only when it rains, there's water. While a perennial stream, that's the Feather River. These two pictures were taken by myself. The Feather Rivers, Plumas County, we did a study on the Feather River many years ago, maybe 30 years ago. We were out there, beautiful river over there. And the other one is the study, the 2008 study that we did in La Leche, Lambayeque. We have many pictures. Ecohydrology. Okay, where does the water come from? Direct precipitation. Surface water, in other words, we can count from 5 reservoirs. Direct precipitation. Surface water or surface runoff. That is in wetlands, ponds, lakes, streams, and rivers. Near subsurface water in the unsaturated so-called vadose zone. This picture was put together by Geological Survey. Fourth, the groundwater, below the groundwater, the water table in the zone of saturation. Mainzer was given the charge of figuring out what was the depth of the groundwater in the western United States, and he came up with the number 27 feet. He said that in his book. Meaning, on the average, if you take the entire western United States, west of I believe, the 105 parallel. 105 parallel is around middle of Colorado, somewhere out there. Okay, west of that, longitude, I guess, parallel, longitude, it's called parallel also. Mainzer said, based on this data, it was 27 feet, which is cool. Certainly much deeper than in the eastern United States where the water is sometimes on the surface, okay? Certainly in Minnesota, for instance, the water's on the surface. Minnesota has 4,000 lakes. They say the state of the 10,000 lakes. It's not 10,000, it's 14,000 lakes. That means the groundwater is on the surface everywhere because it's wet and it's flat and so forth. In other places, maybe less, but there's always a lot of water out there. I don't believe that the East is going to run out of water. I don't think so, really. They'll always be able to find the water. And don't forget that the 100 units of water that precipitate, we're not entitled to the 100. Oh, heck no. The plants are entitled to some of it. The plants take it first. We cannot kill the plants and take their water. That has been proven to be wrong by ARS in the 1970s and 90s. We can get in there, but we're not going to. I don't think we can at this point. Okay, so in other words, the plants have in their own right take their water. So whatever is not used by the plants, then it's used by the animals, and among the animals, the people, right? Humans, but the animals are out there too. So basically, at the end, a very small percentage of the precipitated water we could use from an economic standpoint. I figured it's maybe 10, 20%, not more than that. There's all kinds of stuff out there that require, and they have a right there. We haven't talked about this too much, but it is true, though, that we cannot rely on 100% of the precipitation because it's owned by many other segments of the ecosystem considered in its broad definition. Okay, finally, we did not finish in here. Groundwater. And finally is atmospheric water containing the humidity of the air, partially or fully saturated, the so-called horizontal precipitation. That's a kind of a new subject. It is a new subject because there was not a whole lot of known about this. I know, for instance, being from Peru, that in some areas of the coastal Peru where it never rains, there's still some vegetation. So you wonder, where the water come from? It never rains. And the vegetation is from the condensation of the moisture, because there's humidity, high humidity, and when it gets really cold, it can condense, and then it condenses into whatever material stuff is out there, and then it runs out. Maybe it ran off a little bit. The fact of the matter is that we have vegetation, small patches, but nevertheless vegetation, living vegetation off the coast of Peru where it never rains. So it might have come from somewhere. When I was in Ecuador many years ago, I was told that there was a scientific station built by the Germans that they were looking at. They had instrumented the station for measuring horizontal precipitation. So I went there and visited, took some pictures. It is a fact that this field is ongoing. There's a report out there, by the way. I believe I have the report in Spanish, not in English. I could be wrong on that. And I've actually posted the report. If you're interested in that, I can share that report with you. It's on what the Germans were doing in Ecuador in relation to horizontal precipitation. Okay, figure 4 shows the deep roots of the mesquite. I'm going to try to go fast in here. Precipitation and de facto driver natural systems. Here we go, left. This is interesting. This is an interesting figure. Here, this is what we call the Cerrido in Brazil, but it's right next to a river. Can you see the river in the back? So where's the river? And right next to the riparian condition, you have water. But outside, like this, because it doesn't rain out there, the river's coming from somewhere else, right? So that is, and this one on the other hand, where is this one here? This is in Loja, right? This is where the Germans are doing their work. There's a lot of water out there. Actually, the Germans had calculated that 3,000 millimeters registered on the rain gauge and 3,000 that are condensing from the horizontal precipitation. So the total precipitation on the stem precipitation, the water that is available for the plants is 6,000, not 3,000 millimeters. So that forest out there is a 6,000 millimeter forest. That is why it's so thick. Eco-hydroclimatology, an example of a riparian corridor of coast live oak. These live oaks take a lot of water, and yet I don't see any water there. How can they survive? Because this is the underground water. There is water in there. If you dig in a couple of feet, you're going to find water. You see? So there's where, from that water, is where the coast live oak on the left and on the right get their water. Groundwater pump, or rather groundwater by way of geology and geomorphology has a way of springing up. In this case, this is a case I don't mention in there, but the McCain Valley in Boulevard is a very distinct place, and it's right next to a high mountain. I don't remember the name of it. You can go visit it on Google Earth and you'll see it. And there is a forest out there. How fascinating, a forest in the middle of the desert? Yes, a forest in the middle of the desert. And within that forest, we were lucky enough to visit out there maybe 7, 8 years ago when Alex Costomelki was working with me. That's Alex, one of our students. He got a degree with us, master's degree, in the year 2014. And we were out there and discovered this large specimen of coast live oak. I was really surprised. I didn't think that I had ever seen I should take that back. I've seen wider trees, but not here. And so therefore, we examined this thing and we ended up with the conclusion that there's a stream of groundwater coming from below that has been feeding this tree for at least 300 to 500 years. So if you mess with that stream of groundwater, you're going to mess with the tree. And we said that in this report. Effect of groundwater pumping, I already said that. In the summary, perceived societal need to pump groundwater is constructed with the need of vegetative ecosystems to avail themselves of water from a diversity of sources: precipitation, surface water, subsurface water, groundwater, and the air. In general, plants choose a combination of these sources, depending on the local climate, geology, and geomorphology. Geomorphology is very important. While some plants use several sources, others may rely primarily on only one source. Plants heavily depending on only one source are likely to readily find themselves in moisture stress if that source is substantially reduced or compromised. So we need to look at the whole thing. We need to look at the whole thing. That's why you need an analyst that would know this, his or her eco-hydrology, not just hydrology or not just geology. And that's why we're teaching this stuff. Indiscriminate pumping has the potential to negatively affect the livelihood and survival of vegetative ecosystems that rely primarily on groundwater. The resulting aridization of the landscape may be rarely envisaged. Never mind the global warming effect. Global warming is caused by a whole lot of an array of things. And one of them is messing with the trees, because the trees actually help the control of global warming by taking on the CO2. So if you kill the trees, then it's like you're burning fossil fuels. It's the same effect. We already talked about that in our papers. So I'm going to finish there, and I only have 10 minutes to talk about the impact of the proposal. This paper here, I had to thank God that I had a chance to do this work, because we not only were busy, and I like to be busy for a while, for a year or so, actually a couple of years, because this kept one thing led to another and so forth. We did a lot of studies. We got 12 studies in that region, over a period of 12 years, right? One per year. They're all posted, by the way. And so this is the impact of the proposed Campo landfill on the hydrology of Tierra del Sol. The lady that hired me was opposed to the Campo landfill because it was right next to her property, and she felt that she didn't want to live forever, or however many years she has left, maybe 20, 30 years, next to the landfill. A landfill is a landfill. And it was in a hill, so you were going to see it. You could not help but see it. You woke up in the morning, you see the landfill. It was not going to be hidden at all. Why was it there? Because it was at the end of the Campo Reservation. And the Campo Reservation Indians felt that they could make money by putting this stuff out there. But the Campo Reservation has limits, and they have neighbors, and the neighbors are not Indians. So they could do something like this lady. She's not Indian. She's outside of the reservation. I can show you the map. So this is the issue, that the opposition of the Campo landfill, which by the way was never built. The people of the Campo landfill decided they were going to do the landfill because they needed a way of making money. They have a large area out there. Some of the reservations are large. And there was an edge out there, like the edge. And at the edge, they figured, let's put a landfill in here. Let's get the technologists out here to tell us how to do it. And they hire some of the best technical help, by the way, some of the best geotech guys, because the geotechs get involved in the landfill design. It's a technique. I mean, it's a technology, right? So an issue is the impact that leakage to the landfill liner and the resulting groundwater contamination will have on the hydrology of Tierra del Sol. And we already discussed this, by the way, because we did several projects with them. The focus is the general direction and velocity of the transfer of water and contaminants. The hydrology, here it is, here it is. here's the Campo watershed. I'm sorry, the Tierra del Sol watershed. Actually, the name is not. It's not distinguished, but this is the river that we call the Tierra del Sol channel. This is over here, the river, okay? And the Campo Indian Reservation is over here. Now, the limits of the Campo Indian are over here, and you get over here and over here. So this square over here is the Campo Indian Reservation. Actually, it goes a little further. Anyway, here, it says it right there, Campo Indian Reservation, okay? My boss out there, this lady, whose name I don't want to mention, has a project, not a project, but a ranch over here. A ranch is about 300 acres over here in this area. So they're basically neighbors with the Campo landfill. Okay, and this red over here that you see is the watershed. Is the watershed. And the watershed drains into Mexico. Then it goes into the Tijuana Basin. And then it comes back to the United States because the Tijuana Basin exits into the Pacific Ocean in the United States, like in what is the place? Pacific Beach? No, it's not Pacific Beach. It's down there, the last city before we run into Mexico. I don't remember the name right now, but it exits out there. Very complex, convoluted story, by the way. The Tijuana Basin goes in and out of the United States about 6 times. Into Mexico and back to the United States, back into Mexico, back before exiting into the Pacific Ocean. So how is it that we are going to build a fence over there? It beats reasoning. You can't unless you really want to totally either mess the river, put it on one side, put it on the other side, whatever. The river is kind of encroaching upon the need or the desire for anybody to build a wall out there, okay? So this is the basin, okay, and now I'm gonna go in here, we had to study the precipitation, that's right there, the precipitation. 1993 was an El Nino year, 1998, another El Nino year, 2005 was also El Nino year, right there, El Nino, and El Nino. We know that for a fact. The El Nino recurs every 5 to 7 years, but it does so every 10 or 12, 15 years stronger. Like in this case, the 1993 was very strong. The 1983, we didn't have the data. There was no data because the 83 was stronger than 93. When we had 83, there was a dam, a spillway that broke here in Utah due to the El Nino, because El Nino affects the entire Pacific watershed. Okay. Hydrogeology, we have the hydrogeology in here. They had 3 wells over there in their property where they could figure out what the water level is. These are the wells, one elevation of the wells, okay? You can see the ground level and the elevations. So in order to do a study like this, you have to document the hydrogeology, the geology, everything has to be documented, and we did that. We uncover every stone, by the way. We move every stone. We do that all the time. We don't want to be accused later on of not being comprehensive, because then that's the beginning of your end. We did that in the Pantanal. We did it many places. When we write a report, I hate to tell you this, but people don't argue with us. They can't, because we covered every ground. And you should do that too. Otherwise, people find a hole and they'll dig through the hole and they'll destroy you. Okay, you don't want that to happen. Geologic characteristics. Earthquakes, lots of earthquakes. Look at that. We're located in the arrow, right there. There is where our location is. And it's right next to the earthquake zone coming from the San Andreas, the continuation of the San Andreas. The San Andreas actually come over here, and here it moves inland, and then it comes down. The strongest earthquake in the year 2010 was over here, one of these areas, in the green areas. Actually, the 2010 is not here because this was done before. Mr. Lucky or Dr. Lucky found the largest dike out there in the middle of Tierra del Sol, Turner Ranch. I was over there, we were poking around, looking at the field situation, and I ran into this dike. So I told my host, I said, "What is this?" He says, "Well, there's a dike. There's thousands of them around here." And sure enough, this is a place where there's thousands of dikes, but they're all small. They're like inches, maybe a foot maximum. Well, they're few a foot. This one is 5 feet wide and 1,400 feet long. I had never seen anything like this. That kind of goes on to show there's a lot of tectonism, that at least in the past, tectonism in here. I brought my friend, Professor of Geology over there one day. I said, hey, Monty Marshall, Professor of Geology. I said, Monty, let's go out there. I'll buy you dinner or lunch and you tell me what's going on out there. So I took Monty over here and asked him what was the age of this thing, because they are the ones that in the know. And he said he figured it was 80 to 100 million years. Truly, yeah. Well, that was his guess, his geologic guess. I have no way of guessing. I don't have any frame of reference for this, right? But this is over here in this study. I'm going to go a little, no, I have 5 minutes still. We're going to finish. There is the issue of the lineaments. I remember when I was there, I cannot but mention her name. Donna is her name. Donna said, Professor Ponce, you got to look at the lineaments. I said, the what? She said, the lineaments. I said, no, man, you're going to teach me that. And she said, yeah, we realize that some people are not aware of that. Well, there's lineaments out there. The lineaments are vegetative lineaments that depict fractures. In this area, since it's been geologically active for 100 million years, it has a lot of fractures, okay? So the engineers were out there and they mapped the fractures and they came up with this. Dames and Moore does this. Dames and Moore was a company that used to be around for many years, very well-known geotech company. But then later they were absorbed by some other company 2-3 times. There's been a metamorphosis out there. I don't really know the current name of the old Dames and Moore, but Dames and Moore did this 30 years ago. They plotted, they mapped the lineaments in the location. And as you can see, the water is going to go through from left to right. It's going to seep. Look at this. It's going to seep from, there's a bunch of lineaments over here. It's going to seep from the reservoir, from the footprint of the dump outside, and it eventually gets over here. And this is a watershed, but you know there's connection between watersheds underground. We know that. I think I mentioned to you the other day that we found the runoff coefficient in Mexico that was 1.19, and they can only be explained by the underground rivers, which they have because they have karstic locations out there. So our claim was that this could seep in here, and it will seep, and eventually it gets to the river and so forth, and it goes into Mexico. Interestingly enough, we went into Mexico. We went into this area over here, and we found a river over here with base flow. You could not believe. While the U.S. did not have a base flow, the Mexico had a base flow, and the base flow was coming directly from underground below the fence. I can show you pictures of that. Okay, so there is a hydraulic connection out there, and there is a river. So anyway, hydraulic conductivity, we did an extensive study of this, and you could not believe how many rocks did we uncover in here. Variability and well yield. I do want to read read this report in detail, by the way, because there'll be questions on the exam on this report. I believe this is important. It's extremely important for our class, for environmental hydrology. The hydroecology, the chaparral, the chamis, and the red shank. This is not going to be not going to do justice to us, but when I come back, I may spend 5 minutes on it. The chaparral ecosystem, actually, we don't have time. We did study the vegetation out there. It suffices to say at this time that I hardly knew anything when I went in, and when I came out, I became an expert on chaparral vegetation. The chaparral ecosystem, the chamis and the red shank. The red shank dominates over chamis and higher moisture content. In other words, we found a gradient over there. Where it was dry, it was chamis, and when it was wet, it was red shank. How fascinating. And then we found a huge lineament of red shank. This is the blue elderberry. The blue elderberry is a mesophyte, meaning it likes water. And presumably this is a desert. So where's the water? The water isn't a fracture. There's a fracture out there. And through the fracture, there's water seeping through the fracture. And that is why this plant is over there. We were able to document that in our report. The presence of blue elderberry lined up with the fractures. Those are red points in there are blue elderberry. Okay? And over here, okay, here we go. Then we plotted the lineaments in red, and we had this huge lineament over here, which all the way into Mexico. This is a red shank lineament, meaning it was wet enough so the red shank could get in there and just tell the chaparral to go away, the Chamís chaparral to go away. This is our site. This is our how do you say, our place. So this huge thing, it's a jungle. It's a forest of red shank. It's about 5 miles long, going into Mexico as much. We've looked at it in Mexico. And also, it is about, I would say, 100 feet wide. No, I'm sorry, 1,000 feet wide. I think so. So if you're in there, interestingly, it's very thick, very thick. I don't think I have a picture of it, very thick. So you go in there, you get lost. You can hide. You can hide out there. And I'm going to tell you something that you guys may not know or don't want to hear. But the point is that when the people from other countries jump over the fence, they actually hide in here because they can hide in there. It's a big, thick jungle. Okay, so it's over there. Now we have an infrared in here. You know, infrared shows red. Where it's green, it shows it as red. And in here we got this green. This is our lineament of red shank. So there's two types of red in here. One of them is the lineament of red shank, and the other one is this is riparian. It's coast live oak. The coast live oak over here. Let me see. Yeah, right. So where you see dots in here, there's a huge trees that are right next to the river. There's a river over here, another river over here, and yet a third river over here. They are ephemeral. They don't have any water. And over here on top, there's some reds in there because of the fact that there's fractures. Wherever there's fractures, there's red, because this whole thing is rock. This is what is called a rock aquifer. It's not alluvial. It's a rock aquifer. Okay? So stream morphology. Oh, okay, here we go. And I'm going to ask for a couple more minutes here. This is the dike that I shown you. The dike and a spring. The spring is right below the dike. The dike is coming from the mountains because there's mountains over here. There is a difference in elevation, and it comes into the river. And right there, there's a spring over there. There's the spring. Can you see? Right in there, there's a live oak, a specimen of live oak, well positioned to drink the water that's coming from the dike. And as it goes in here, you can see the water is seeping from the ground. So much that the people out there have actually put this tub in there for the reason to collect the water so that the animals can drink it. How fascinating. Okay. Groundwater hydraulics, I'm not going to get in there, but I do want you to read it. Extensive and very well detailed. In the conclusions, we have hydrology, hydrogeology, hydroecology, stream morphology, and groundwater hydraulics. And that's the end of this. And finally, we show a spring. We documented about 13 springs, depending on the time of the year, and depending on the year too, because the springs are multi-annual. Sometimes when it rains a whole lot, you not only have 13 springs, you have 35 or 50 springs out there. We have a video from year 1994. I believe I may have posted that video, and if not, I'm going to write it in here to post it for you. The video 1994. No, 1993, excuse me. It rained so much out there throughout the entire neighborhood and the entire region, even Tijuana. Tijuana, there was a huge flood in here, because Tijuana is very close, right? And this place out here, it had artesian flow. What does that mean? That there were pipes on the ground and the water was popping out of the ground and going up the pipes and flowing out as if it were a fountain. How did that happen? Well, that happened because the entire reservoir filled and it was starting, there's a lot of pressure out there, and since it's an aquifer, the pressure, you don't exactly know where the pressure is, depends on the conduction, depends on the seeps and so forth. So I'm going to finish in there. Fascinating study, which I was lucky to conduct with all kinds of endnotes, interesting endnotes out there. So with that, be my guest, take a look at this. There'll be questions on the exam on this paper. Thank you very much. So I'm going to stop there. Today is Thursday. Next week, we are going to be getting into a different subject. I believe the subject next week is salinity. Thank you very much. Where's Professor Ponce in here? Oh, there it is. That's me. I'll see you next Tuesday at the usual time.